I do theoretical physics, and what I have been asking mostly myself for 20 years and more is how to write a quantum theory of gravity. But this has raised other questions. And in particular, we do have today some theories of gravity. I've been working on a theory of gravity which is loop quantum gravity, or loop gravity, which might work, is not complete, has some aspect of it which are not clear, or it might not work. But in the way it is formulated, it challenges basic notions about space and time, and it requires us to ask questions about space and time. Now, so the question becomes larger because it becomes what is space and what is time. But I think the question I've been asking most to myself recently is larger still, and is what do we really do when we do science? What is science? That's a large question, and I guess this is what I want to talk about in this chat. We teach our students. We say that science is. We have some theories about science. Science is about the hypothetical-deductive methods. We have observations. We have data. The data requires to be organized in a theory, so then we have theories. These theories are suggested or produced from the data somehow, then checked in terms of the data, and then time passes, we have more data, theories evolve, we throw away a theory, we find another theory which is better understanding of this data, and so on and so forth. This is a standard idea of how science works, which implies that science about empirical content, the true interesting, relevant content of science is empirical content. Since theories change, the empirical content is the solid part of what science is. Now, there's something disturbing for me as a theoretical scientist in all this. I feel that something is missing. Something of the story is missing. And I've been asking to myself, what is this thing missing? I'm not sure I have the answer, but I want to present some ideas on something else which science is. And I think this is particularly relevant today in science and in particular in physics because if I'm allowed to be polemical, in my field, in theoretical physics, it is 30 years that we fail. There hasn't been a major success in theoretical physics in the last few decades after the Standard Model somehow. Of course, there are ideas. These ideas might turn out to be right. I mean, loop quantum gravity might turn out to be right or not. String theory might turn out to be right or not. But we don't know, and for the moment, they have not. Nature has not said yes in any sense. And it might be, I suspect that this might be in part because of the wrong ideas we have about science. And because methodologically we are doing something wrong, at least in theoretical physics, perhaps also in other sciences, I don't know. So let me tell you a story to explain what I mean. And the story is an old story about what I see, what my sort of latest, greatest passion outside theoretical physics, which is an ancient scientist, I would say, even if often is called a philosopher, which is Anaximander. I've got fascinated by this character, Anaximander, and I went into understanding what he did, and to me, he's a scientist, and he did something which is very typical of science, and which shows some aspect of what science is. So what is the story with Anaximander? It's the following in brief. Until him, all the civilizations of the planet, everybody around the world, thought that the structure of the world was the sky over our head and the earth under our feet. So there's an up and down, heavy things fall from the up to the down, and that's reality. The reality is it's oriented up and down, heavens up and earth down. Then comes Anaximander and says, no, something else. The earth is a finite body that floats in space without falling, and the sky is not over our head, it's all around. And how he gets it? Well, obviously, I mean, you look at the sky, you see things going around, the star, the heavens, the moon, the planets, everything moves around and keeps turning around us. So it's sort of reasonable to think that below us there's nothing. So it seems simple to get to this conclusion, except that nobody else got to this conclusion. I mean, in centuries and centuries of ancient civilizations, nobody got there. The Chinese didn't get there until the 17th centuries, when Matteo Ricci and the Jesuits went to China and told them, in spite of centuries of imperial astronomical institute that were studying the sky. The Indians only learned it when the Greek arrived to tell them. The Africans, in America, in Australia, somehow nobody else got to this simple realization that the sky is not just over our head; it's also under our feet. So why? Because obviously, it's easy to suggest that the Earth sort of floats into nothing, but then you have to ask the question: why doesn't it fall? And the genius of Anaximander was to answer this question. We know his answer from Aristotle, from other people. He says, he doesn't answer this question, in fact. He questions this question. He says, why should it fall? Things fall toward the earth. Why the earth itself should fall? In other words, he realizes that the obvious generalization from every small, heavy object fall to the earth itself falls, it might be wrong. And he proposes some alternative, which is just the objects falls toward the earth, which means that the direction of falling changes around the earth. This means that up and down become notions relative to the earth, which is rather simple to figure it out for us now, which we've learned this idea. But if you think at the difficulty when we were children to understand how people in Sydney could live upside down, clearly requires some changing in something structural in our basic language in terms of which we understand the world. In other words, up and down means something different before and after Anaximander revolution. He understands something about reality essentially by changing something in the conceptual structure that we have in grasping reality. In doing so, he is not doing a theory. He's understanding something which in some precise sense is forever. It's some uncovered truth, which to a large extent is a negative truth. He frees ourselves from a prejudice which was ingrained in the conceptual structure we had for thinking about space. Now, why I think this is interesting? Because I think that this is what happens at every major step, at least in physics, and but in fact I think this is what happened at every step, even not major. When I give a thesis to a student, most of the time the problem I give for a thesis is not solved. It's not solved because the solution of the question most of the time is not solving the question, it's just questioning the question itself, and realizing that in the way the problem was formulated there was some implicit prejudice assumption which was the one to be dropped. But if this is so, the idea that we have data and theories, and then we have a sort of rational agent that constructs theories on the data using his rationality, his mind, his intelligence, his conceptual structure, and so juggling with theories and data, doesn't make any sense. Because what is being challenged at every step is not the theory, is the the conceptual structure used in constructing theories and interpreting the data. In other words, it's not changing theories that we go ahead, but changing the way we think about the world. The prototype of this way of thinking, I think the example that makes it more clear is Einstein's discovery of special relativity. On the one hand, there was Newtonian mechanics, which was extremely successful. On the other hand, with its empirical content. And there was Maxwell theory with its empirical content, extremely successful, the two. But there's a contradiction between the two. Now, if Einstein had gone to school and learned what science is, if he had read Kuhn and the philosopher explained what science is, if he was any one of my colleagues today who are looking for a solution of the big problem of physics today, what would he do? He would say, okay, the empirical content is a strong part of the theory. The idea in classical mechanics that velocity is relative, forget about it. The Maxwell equation, forget about them, because this is a volatile part of our knowledge. The theories themselves have to be changed. Okay, what we keep solid is the data, and we modify the theory so that they make sense coherently. They would make sense coherently of the data. That's not at all what Einstein does. Einstein does the contrary. He takes the theory very seriously. He believes the theory, and he says, look, classical mechanics is so successful that when it says that velocity is relative, we should take it seriously. We should believe it. And the Maxwell equations are so successful that we should believe the Maxwell equations. He has so much trust in the theory itself, in the qualitative content of the theory. That qualitative content that Kuhn says changes all the time, that we are learned not to take too seriously. So much faith in this, confidence in that he's ready to do what? To force a coherence between these two, the two theories, by challenging something completely different, which is something in our head, which is how we think about time. So he's changing something in common sense, something about the elementary structure in terms of which we think the world, on the basis of the trust of the past results in physics. It is exactly the opposite of what is done today in physics. If you read Physical Review today, it's all about theories that challenge completely and deeply the content of previous theories. So theories in which is not Lorentz invariants, which are not relativistic, which are not Jerry covariant, quantum mechanics might be wrong. Every physicist today is immediately ready to say, okay, all our past knowledge about the world is wrong. Let's randomly pick some new idea. And I suspect that this is not a small component of the long-term unsuccess of theoretical physics. You understand something new about the world, either from new data that arrive, or from thinking deeply on what we have already learned about the world. But thinking deeply means also accepting what we've learned, challenging what we think, and knowing that in an ensemble of things that we think, there may be something to modify and to change. So, what are then the aspects of doing science which I think are under evaluated and should come up front? First, science is about constructing visions of the world, about rearranging our conceptual structure, about creating new concepts which were not there before, and even more about changing challenging a priori that we have. So it's nothing to do about the ensemble of data and the way of organizing the ensemble of data. It has everything to do about the way we think and about our mental vision of the world. Science, I think, is a process in which we keep exploring way of thinking and changing our image of the world, our vision of the world, to find new one that sort of works a little bit better. And in doing that, what we have learned in the past, it's our main ingredient, especially the negative things we have learned. If we have learned that the Earth is not flat, there will be no theory in the future in which the Earth is going to be flat back. If we have learned that the Earth is not at the center of the universe, that's forever. It's not going to, we're not going to go back to a theory. If we have learned that simultaneity with Einstein is relative, we're not going back to an absolute simultaneity, like many people think. And this means that when an experiment measures a neutrino going faster than light, we should be very suspicious and, of course, check and see whether there is something very deep that is happening. But it's absurd that everybody jumps and say, okay, Einstein was wrong, there's a little anomaly that shows. That's not the way. It's never worked like that in science. The past knowledge is always with us and is our main ingredient for understanding the future. The theories, the theoretical ideas which are based on, let's imagine that this may happen because why not, I think are not taking us anywhere. Now, I seem to be saying two things contradictory. On the one hand, we trust the knowledge, and on the other hand, we are always ready to modify in depth part of our conceptual structure about the world. There's no contradiction between that, I think, because the idea of the contradiction comes from what I see as sort of the deepest misunderstanding about science, which is the idea that science is about certainty. Science is not about certainty. Science is about finding the most reliable way of thinking at the present level of knowledge. Science is extremely reliable, it's not certain. In fact, not only is it not certain, but it's the lack of certainty that founds it, that grounds it. Scientific ideas are credible not because they are sure, but because they are the ones that have survived all the possible critics of the past, and they are the more credible because they are, open down there, put on the table for everybody's criticism and for finding new ones. But the very expression scientifically proven is a contradiction in terms. There's nothing which is scientifically proven. I think the core of science is the deep awareness that we have wrong ideas, we have prejudices, and we have ingrained prejudices. In our conceptual structure for grasping reality, there might be something non-appropriate, something we may have to revise to understand better. So at any moment, we have a vision of reality, which is effective, is good, is the best we have found so far, so it's the most credible we have found so far. But it is mostly correct. I mean, the Earth is not in the center of the world, it's true. But at the same time, is not taken for certain, and any element of it is a priori open from the vision. I think this is why do we have with this continuous. On the one hand, we have this brain, right, because it has evolved in the millions of years, and it has evolved for us for being basically run in the savannah and run after eat deers and try not to be eaten by lions. So we have a brain which is tuned to meters and hours, which is not particularly well tuned to things about atoms and galaxies. So we have to get out of that. But at the same time, I think we've been selected for being going out of the forest, perhaps going out of Africa, for being as smart as possible as animals that escape lions. So this continuous effort that is part of us to change our own way of thinking, to readapt, is very part of our nature. We are not changing our mind away from nature. It's our natural history that continues to change that. And if I make a final comment about this way of thinking about science, or two final comments. One is that science is not about the data. The empirical content of scientific theory is not what is relevant. The data serves to suggest us the theory, to confirm the theory, to disconfirm the theory, to prove the theory wrong. But these are the tools that we use. What interests us is the content of the theory. What interests us is what the theory says about the world. The general relativity says space-time is curved. The data of general relativity are that Mercury perihelion moves 43 degrees per century with respect to that computed with Newtonian mechanics. Who cares? Okay? Who cares about these details? If that was the content of general relativity would be boring. General relativity is interesting not because of its data, but because it tells us that as far as we know today, the best way of conceptualizing space-time is a curved object. So it gives us a better way of grasping reality than Newtonian mechanics, because it tells us that there can be black holes, because it tells us there's a Big Bang. This is the content of the scientific theory. All living beings on Earth have common ancestors. This is the content of scientific theory, not the specific data used to check the theory. So the focus of scientific thinking, I believe, should be on the content of the theory, the past theory, the previous theories, try to see what they hold concretely and what they suggest us for changing in our conceptual framing themselves. And the final consideration regards just one comment about this understanding of science and this long conflict that has crossed the centuries between scientific thinking and religious thinking. I think often it is misunderstood. The question is why can't we live happily together, and why can't people pray their gods and study the universe without this continuous clash? That I think that this continuous clash, it's a little bit unavoidable for the opposite reason of the one often presented. Is unavoidable not because science pretends to know the answers, but it's the other way around. Because if scientific thinking is this, then it is a constant reminder to ourselves that we don't know the answers. And in religious thinking, often this is unacceptable. So what is unacceptable is not a scientist that says I know, but is a scientist that says I don't know, and how could you know? There is, at least in many religions, in some religions, or in some ways of being religious, an idea that there should be truth that one can hold upon and not be questioned. And this way of thinking is naturally disturbed by a way of thinking which is based on continuous revision of even, not of the theories, of even the core ground of the way in which we think. So, summarizing, I think science is not about data, it's not about empirical content, it's about our vision of the world, it's about overcoming our own ideas and about going beyond common sense continuously. Science is a continuous challenge of common sense, and the core of science is not certainty, is continuous uncertainty, and I would even say the joy of taking what we think, being aware that in everything we think there are probably still an enormous amount of prejudices and mistakes, and try to learn to look little bit larger, and knowing that there's always a larger point of view that we'll expect back in the future. So we are very far from the final theory of the world in my field in physics, I think, extremely far. Every hope of saying, well, we're almost there, we've solved all the problem, is nonsense. And we are very wrong when we discard the value of theories like quantum mechanics, general relativity, or special relativity for that matter, and throw them away trying something else randomly. It's on the basis of what we know we should learn something more, and at the same time we should somehow, I think, take our vision for what it is, a vision which is the best vision that we have, but a continuously evolving vision.
Great.
If this is science, if science works or in part works in the way I've described, if this which I've described is part, it's some relevant aspect of the way science works. This is strongly tied to the kind of physics I do. The way I view the present situation in fundamental physics is there are different problems in fundamental physics. One is a problem of unification, so writing big theory of everything. And a more specific problem, which is a problem which I work, is quantum gravity. Quantum gravity means just simply doing the quantum theory of gravity, of how things fall, the gravitational field. But it's a remarkable problem because because of general relativity, gravity is space-time. That's what we have learned with Einstein. Doing quantum gravity means understanding what is quantum space-time. And quantum space-time precisely requires some key change in the way we think about space and time. Now, with respect to quantum gravity, in my opinion, there are two major research directions today, which is the one in which I work, loops and strings. And they are not only different as not just two different set of equations, but they are based on different philosophy of science in one sense. The ones in which I work is very much based on the philosophy I just described, and that somehow what forced me to think about philosophy of science. Why? Because the idea is the following. The best we know about space-time is what we know from general relativity. The best we know about quantum mechanics is what we know from quantum mechanics. There seems to be a difficulty in attaching the two pieces of the puzzle together, which is to turn them around, they don't fit well. But the difficulty might be in the way we face the problem. The best information we have about the world is still contained in these two theories. So let's take quantum mechanics as seriously as possible, so believe it as much as possible, maybe enlarging a little bit to make it general relativistic or whatever, and let's take general relativity as serious as possible. General relativity has peculiar feature, specific symmetries, specific characteristic. Let's try to understand them deeply and see as they are, or maybe just a little bit enlarged, a little bit adapted, can fit with quantum mechanics to give a theory. Even if the theory that comes out then contradicts something which is the way we think. That's the way quantum gravity, in the way of the loops, the way I work in, the way many other people work in, is being developed. And this takes us in one specific direction of research, a set of equations, a way of putting up the theory. String theory has gone in the opposite direction. In a sense, it says, well, let's not take too seriously general relativity as an indication of how the universe works. Let's try, even quantum mechanics is being questioned to some extent. Let's maybe imagine that quantum mechanics has to be replaced by something very different. And let's try to guess something completely new, which is some big theory, out of which somehow the same empirical content of general relativity and quantum mechanics come out in some limit. I am distrustful of this huge ambition because we don't have the tools to guess this immense theory. String theory is a beautiful theory. It might work, but I suspect it's not going to work. And I suspect it's not going to work because it's not sufficiently grounded in everything we know so far in about the world, and especially in what I think or perceive as the main physical content of generativity. String theory is a big guesswork. I think physics has never been a guesswork, has been a way of unlearning how to think about something and learning about how to think it a little bit different, but reading the novelty into the details of what we already know. Copernicus didn't have any new data, any major new idea. He just took Ptolemy in the details of Ptolemy, and he read in the details of Ptolemy the fact that the equants, the epicycles, the deferents were in certain proportions between them, the way to look at the same construction from a slightly different perspective and discover the Earth is not the center of the universe. Einstein, as I said, took seriously Maxwell theory and classical mechanics to get special relativity. So loop quantum gravity is an attempt to do the same thing. Take seriously general relativity, take seriously quantum mechanics, and out of that, bring them together, even if this means a theory where there is no time, no fundamental time, so we have to rethink the world without basic time. So the theory on the one hand is very conservative because it's based on what we know, and it's totally radical because it forces to change something deep in our way of thinking. String theorists think different. They say, well, let's go at infinity where somehow the covariance of general relativity is not there. Now we know what is time, we know what is space, because we are on symptotic distances, at large distances. So the theory is more wild, more different, more new, but in my opinion is more based on the old conceptual structure. It's attached to the old conceptual structure and not attached to the content of the novel content of the theory that have proven them empirically successful. That's how my way of reading science sort of matches with the specific of the research work that I do, and specific of loop quantum gravity. Of course, we don't know. I mean, I want to be very clear. I think that string theory is a great attempt to go ahead, done by great people. My only polemical attitude with string theory is when I hear, but I hear less and less now, when I hear, oh, we know the solution already, is certainly string theory. That's certainly wrong and false. What is true is that that's a good set of ideas. Loop quantum gravity is another good set of ideas. We have to wait and see which one of the theory turns out to work and ultimately to be empirically confirmed. This may take me to another point, which is, should a scientist think about philosophy or not? And it's sort of fashion today to discard philosophy, to say, now we have science, we don't need philosophy. And I find this attitude very naive, because for two reasons. One is historical, just look back. I mean, Heisenberg would have never done quantum mechanics without being full of philosophy. Einstein would have never done relativity without having read all the philosopher and the head full of philosophy. Galileo would never have done what he has done without having the head full of Plato. Newton thought of himself as a philosopher and started by discussing with Descartes and had strong philosophical ideas. So, but even Maxwell, Boltzmann, I mean, all the major steps of science in the past were done by people who were very aware of methodological, fundamental, even metaphysical questions being posed. When Heisenberg does quantum mechanics, he is in a completely philosophical mind. He says in classical mechanics there's something philosophically wrong, there's not enough emphasis on empiricism, and so it is exactly these philosophical readings of him that allow him to construct this fantastically new physical theory, scientific theory, which is quantum mechanics. The divorce between this strict dialogue between philosophers and scientists is very recent, and somehow it's after the war, after in the second half of the of the 20th century, and it has worked because in the first half of the 20th century, people were so smart. So Einstein and Heisenberg and Dirac and company put together relativity and quantum theory, and did all the conceptual work. The physics of the second half of the century has been, in a sense, a physics of application of the great ideas of the people of the 30s, of the Einstein and the Heisenbergs. And when you want to apply this idea, when you do atomic physics, you need less conceptual thinking. But now we are back to the basics, in a sense. When we do quantum gravity, it's not just application. And I think that the philosophers who say, the scientists who say, I don't care about philosopher, it's not true that they don't care about philosophy. It's that they have a philosophy. They are using a philosophy of science. They are applying a methodology. They have their head full of ideas about what is the philosophy they're using. It's just they're not aware of them, and they take them for granted as if this was obvious and clear, when it's far from obvious and clear. And they're just taking a position without knowing that there are many other possibilities around which might work much better and might be more interesting from them. So I think there is a narrow-mindedness if I may say so, in many of my colleagues, scientists, that don't want to learn what is being said in philosophy of science, and there is also narrow-mindedness in a lot of probably areas of philosophy and humanities which they don't want to learn about science, which is even more narrow-minded. Somehow, culture is rich and large, and I mean, this is probably I'm throwing down an open door if I say it here, but restricting our vision of reality today on just the core content of science, on the core content or the core content of the humanities, is just being blind to the complexity of reality that we can grasp from a number of points of view. Which talk to one another enormously, and which I believe can teach one another enormously.